Alright, today we're going to do a short video here to do just a brief introduction and demo of a solid-state dip meter. This is a more modern version of a meter that's been around for ages called a grid dip meter. And really what it is, and it's over sitting here in this box, is a meter that is essentially a variable oscillator. Okay, and you can adjust the frequency of the oscillation on the dial here. And then you adjust the range that you're going to adjust it over by these various plug-in coils. Each of these coils covers a specific frequency range. We look at this coil here, it says 1.6 to 3.4 megahertz, and so on, up to this one here. The highest one here that I've got is 100 megahertz to 250 megahertz. Okay, so each of these kind of covers some overlapping ranges up from, from HF up to some VHF frequencies. Okay, and the idea is that the meter is an oscillator, and you turn it on, you can adjust the signal strength of the oscillation, and you can couple it to circuits. And the most common use for a grid dip meter, or a dip meter like this, or a dipper, is to couple it to a circuit to measure its resonant frequency. Because the way this meter works is that as you couple the energy from this meter to a circuit under test, as you adjust the frequency and pass through the resonant frequency of the circuit that you're testing, you will notice a dip in the meter, because the meter is measuring the strength of oscillation. When you couple into a circuit that is resonant at that frequency, it's going to reduce the level of oscillation in the meter, because it basically represents a load at that frequency, and you'll notice the dip in the meter. And the old grid dip meters, it was actually a dip in grid current for the oscillator. In the case of the solid-state meters, it's a dip as that's noticed in a detector. It's basically an oscillator and a detector, and you're measuring the output of the detector here. Okay, so let's take a quick look at how you could use this to look at resonant circuits. So a brief little view of that. If you have an LC circuit like this, either series or parallel, the circuit is resonant when the capacitive and inductive reactance are equal. Okay, so it really kind of comes down to this, that you can actually calculate, if you know the capacitance and inductance, you can calculate resonant frequency with this formula. You can rearrange this formula to be able to calculate a capacitance, an unknown capacitance or inductance, if you have the other one being known. By simply constructing that circuit, maybe with your known capacitance and unknown inductance, okay, you can construct the circuit, use the dip meter to find where that's resonant, and then plug in that resonant frequency, the known capacitor value, calculate this out, and figure out what that unknown inductor is. So let's show you real quickly how we can do this with a resonant circuit. Okay, so what we'll do is we'll take the meter here, and I'm going to select a coil. I happen to know which one I'll need for this. This happens to be a 12.5 megahertz to 26 megahertz coil, and we'll stick that in the RCA jack there in the front. Okay, so here's the circuit I'm actually going to look at. This happens to be a 0.22 microhenry inductor, with a little molded inductor there, and a 220 picofarad capacitor. And if you run through the math on this, you'll find that this will oscillate, or resonate I should say, at approximately 22.5, 22.7, 22.8 megahertz. Okay, so let's go take a look at that. Now what we'll want to do is couple these inductors together. You don't want to kind of go crossways. You want the coils to kind of be parallel to each other, so either like this or in line. And what I did is I put a little J hook on the end of this coil, so I can kind of stick it right into the coil here, so that it kind of do this with one hand. So what we'll do is we turn the meter on, okay, and we can adjust the oscillation level, okay, to get a reasonable value. Okay, we'll just kind of get up about 70% here. And now we adjust the frequency. Okay, now in this case, the coil we selected is actually the green coil, so we're looking at the green scale here. Okay, and as we adjust the frequency of the oscillator, we can take a look at what the meter's doing. Okay, and you'll notice I'm rotating this up. Watch the meter, and as I pass through resonant frequency, the meter dips, and now it comes back up again. So I'm keeping going up, and now it's going back up. Let me come back down in frequency. Okay, I dipped, came back up. And that's really how you use this. You find that frequency of that dip, and it's right about there. Okay, and we take a look at the scale here. Okay, it's showing between 22 and 23 megahertz. Okay, now these scales you can't really get better than maybe even a couple of percent, 2 or 3, maybe 5% accuracy. So we'll call that between 22 and 23 megahertz, which is what we expect. We expect about 22.7, 22.8 with that component combination. Now what we can do is actually take a look at what frequency this is actually generating. What I'll do is I'll take one of my other coils. Okay, it's just a convenient little coil of wire. And if I take and couple that into my frequency counter here, all right, we can come back down here, take the dip meter. Let me remove my circuit under test. And so this thing is still oscillating. And if I take this and couple this coil to my test coil here, I can see I've got about 22.77 megahertz. Okay. In fact, we could actually see this thing is actually oscillating. If I take this same coil and I couple it down into, you can see I've got my little scope probe here, just kind of looped together. If I stick that coil inside there, I can actually see on the scope, there's my signal, okay, on the scope, okay. And let me take a look carefully. Let me turn the brightness down on this poor scope here. There we go. And now if we bring this back up here, okay, we can actually see the sinusoidal oscillation of this thing as I stick it in the coil. And you can see I've got the cursors kind of marked out there, so it's showing me that same 22.7, 22.8 megahertz oscillation. Okay, so there's one quick example of how to use this meter to measure the resonant frequency of a circuit. Now you might be working on a radio or something like that. You can get right down there and couple this coil to, you know, the IF cans and things like that to try to measure frequency. So that brings up a couple of applications. You know, one is, let's say you built an antenna. You want to measure the resonant frequency of the antenna. You would build yourself a couple little loops at the end of your coax, or even just directly couple this to the antenna itself and measure resonant frequency by looking for a dip. You could look at things like quarter wave transmission lines to find out at what frequency is that a quarter wave transmission line, because they represent some resonant properties. You can use it to find unknown capacitors and inductor values if you have a set of known values to kind of couple them up with. You can also use this thing as a signal source. As we can see, you know, when I couple this thing here into the scope, you know, this is obviously a signal source. It's generating a signal. So you might use this to couple energy into, say, a radio you're working on, or couple it into an antenna to be sure that the signal is working right. Now, that's all of these examples are using the dip meter in a mode called a signal injection mode. You also have the ability of turning the oscillation all the way down till it just turns off, and that turns the meter now into an absorptive wave meter. What that means is that the detector now is hooked up to a nice tuned circuit. So as you couple the coil or the meter to a circuit that's running, okay, and then tune that tuned circuit, you can get a positive deflection on the meter whenever you pass by, you know, the frequency that this signal or this coil is picking up, okay, and you're only going to get that deflection when you pass right through that frequency, so you'll be able to read off the frequency. So again, say you're working on a radio and maybe the local oscillator, you know, may or may not be running. You can actually couple into that one of the coils inside of that local oscillator and tune this as an absorptive wave meter to see if that local oscillator is running at the frequency you think it should be. Okay, so another handy use for that. You could couple, you know, for example, if you want to measure, you know, a coil or a crystal, you can couple of turns against that, couple that to the meter and adjust. Now I'll caution you that measuring something like a crystal, these are very, very high Q devices, so you got to be really, really slow when you're adjusting this, otherwise you'll zip right through the resonant frequency there, and it might be tough to see. But that's a couple of quick uses of how you could use a solid state dip meter or an old grid dip meter for looking at resonant circuits, getting some unknown, determining some values of some unknown inductors and capacitors, looking at resonant properties of, you know, LC circuits, resonant circuits, antennas, etc. But it's a fun little meter, can do a lot for you, and you just don't see them much anymore, but I thought it'd be a neat thing to do a video on. So I hope you enjoyed it and learned a little something. And comments and suggestions and questions are always welcome. Thank you.